Usually when we think about numbers, we just sort of picture them sitting neatly in a spreadsheet or, I don't know, a textbook.
Right, like they're just cold, hard, objective facts.
Exactly. Like you see 5, it means 5. It feels incredibly straightforward.
Yeah, but it creates this illusion of absolute certainty. The human brain naturally assumes that because the raw math is objective, the way we perceive it must be objective too.
Which is wild, because then you take those exact same numbers and you draw them. You make them into like a line graph or a bar chart, and suddenly that straightforward math becomes totally vulnerable to all sorts of manipulation.
Oh, absolutely. Misinterpretation, manipulation, you name it.
Which brings us to our mission today. We are taking you, the curious learner, on this really comprehensive journey into the art of interpreting visual data.
Because it really is an art.
It is. And we're specifically targeting the mechanics of reading charts and graphs, which, is a massive hurdle if you are prepping for the TEAS or HESI nursing entrance exams.
Right, because it's heavily tested.
Yeah, so we have a stack of sources today. It's this fascinating mix of cognitive science, history, and test prep strategy to show you exactly how to extract the truth from a graph without, falling for the traps.
And I think the foundational idea here is something researchers call graphicacy.
Graphicacy.
Yeah, it's a term that was introduced back in the 1960s by these British geographers, Balchin and Coleman.
Okay.
They argued that the ability to understand and communicate information through visual charts is this distinct, highly specific spatial reasoning skill.
Interesting.
It is not just a byproduct of being good at math.
Right.
It sits right alongside literacy for reading words and, numeracy for calculations.
Okay, let's unpack this because that is a massive paradigm shift.
It really is.
I mean, the old assumption was just that if you understand the numbers, the picture is just like a nice little bonus.
Right, just decoration.
Yeah, but treating graphicacy as its own discipline makes total sense. It's like assuming that just because you know the alphabet, you automatically know how to read a topological map.
Oh, that's a great way to put it.
They use the same letters, sure, but the spatial arrangement requires an entirely different cognitive process.
And that spatial arrangement is exactly why cognitive researchers in the late 20th century proved that you can be a mathematical genius and still completely misinterpret a bar chart.
Wait, really? A genius can get a bar chart wrong?
Absolutely, because when you look at a graph, your brain isn't just crunching numbers, it's making these rapid, unconscious, perceptual judgments about length, area, color, angle.
And that explains why nursing entrance exams test this as a dedicated competency. They aren't just checking if you can add or subtract. They are testing your perceptual judgment.
Exactly.
So if graphicacy is this distinct skill, where did the tools we're actually reading come from? Because, the line graph didn't just fall out of the sky.
No, it didn't. The origin story is surprisingly practical, actually. We have to look back to late 18th century Scotland.
All right.
There was this engineer and political economist named William Playfair.
Playfair, right.
Yeah, and he was dealing with decades of data regarding England's trade balances, imports, exports, just these massive walls of numbers.
Ugh, I can just imagine a merchant or a politician looking at a 50-page table of trade figures and just giving up.
Right, the cognitive load is way too high.
Yeah, you just glaze over.
That was Playfair's exact realization. Human working memory just cannot hold on to 50 distinct data points to spot a long-term trend.
It's impossible.
So in 1786, he essentially invented the modern line graph and the bar chart.
Wow.
By turning those numbers into physical lines on a page, he offloaded the cognitive work from the brain's working memory directly to its visual processing center.
So you didn't have to calculate the trend.
Exactly. You could just look at the slope of the line. And then a few years later, in 1801, he introduced the pie chart to show the relative land area of European empires.
Okay, but taking data and making it digestible is one thing. But the sources highlight someone who took Playfair's concept and transformed it into an active tool for persuasion.
Florence Nightingale.
Yes, Florence Nightingale, during the Crimean War in the 1850s.
Her contribution fundamentally changed how we viewed data. Nightingale was, she was collecting mortality statistics at a British military hospital.
And the conditions were horrific. Right?
Beyond horrific. But the raw numbers were not convincing Parliament to fund sanitary reform. Politicians would look at the mortality ledgers and simply dismiss the deaths as just, the inevitable cost of war.
Right, just numbers on a page. So she created her famous coxcomb diagram.
Yes.
She divided each month of the war into colored wedges, like Red represented combat wounds, black for other causes,
Right.
and then she used this massive blue wedge to represent deaths from preventable diseases and poor sanitation.
And the visual impact was just undeniable. When you look at our diagram, the blue wedges absolutely dwarf the red ones.
Not even close.
No. She proved visually that the hospital conditions were killing far more soldiers than the enemy combatants were.
She turned a graph from a passive tally into a literal life or death argument. Like, you cannot unsee that massive blue wedge.
You really can't.
And looking at the nursing exams today, is this why graphicacy is still a core competency? Because a nurse isn't just logging numbers. They're evaluating a patient's status to make a clinical argument.
That is the direct lineage, yeah. Nightingale, who actually had formal training in statistics, she proved that a graph is an active form of reasoning.
Wow.
And if you fast forward to modern cognitive science, researchers like Jacques Bertin and Colin Ware categorize this reasoning into 3 distinct levels of graph comprehension.
Okay, what are the 3 levels?
Level 1 is elementary reading. You are just extracting a single data point.
Like looking at a patient's chart and answering, what was the heart rate at 2 p.m.? It's just a visual scavenger hunt.
Precisely. It requires very little cognitive effort. But level 2 is reading between the data.
Between the data.
Yeah, this requires you to hold multiple points in your working memory to compare them or calculate a relationship, like how much did the heart rate increase between 2 p.m. and 4 p.m.?
Ah, okay. And then level 3 is reading beyond the data.
Right. Extrapolating, finding the underlying pattern, and making an inference. Like, based on this 4-hour trend, is the patient stabilizing or crashing?
So the TEAS and HESI exams, they must test all of these.
They're designed to aggressively target levels 2 and 3.
Really aggressively.
Oh, yeah. Knowing where the numbers live on the page is entirely insufficient. You have to decode the visual relationships, which is exactly where the test designers lay out their traps.
Okay, so if these exams are testing those higher levels of reading, how do we actually decode these visuals without falling for those traps?
We have to get into the core mechanics.
Let's do it. The foundation of any standard chart is the axis, right?
Right.
The classic horizontal x-axis and vertical y-axis.
Yes. The x-axis conventionally displays the independent variable.
The independent variable.
Right. That is the factor you are controlling or tracking as a reference. So like time, age groups, medication dosage.
Stuff that stands on its own.
Exactly. And the axis displays the dependent variable. That is the outcome you're measuring to see how it responds.
Like blood pressure, weight, or the number of patients admitted.
You got it.
Which brings up the first major trap I really want to highlight for everyone listening. It's the assumption that a physically bigger bar on a chart always means a proportionally bigger value.
Oh, this is a classic trap.
Right. You see a bar that is twice as tall as the one next to it, and your brain instantly translates that to, oh, double the amount.
The visual processing center of your brain jumps to that conclusion automatically. But, and this is crucial, that visual shortcut is only mathematically true if the y-axis starts at 0.
If it starts at 0.
Yes. If the creator of the graph truncates the axis, say, starting it at 50 instead of 0, a bar representing the number 60 will look massive compared to a bar representing 55.
I always like to think of a truncated axis like looking at an object through a really powerful magnifying glass.
Oh, I like that.
Yeah, like the glass zooms in so closely on a tiny 1-inch pebble that it fills your entire field of vision, making it look like a massive boulder. It hides all the context of the ground around it.
Exactly. A 10% actual difference in the data can be stretched to look like a 300% visual difference.
It's crazy.
If you don't manually check the scale, your eyes will lie to you.
That context is just entirely removed.
It is. Now, another crucial mechanic the exams test is understanding the nature of the data itself, because that dictates the type of graph you use. There is a rigid distinction between continuous data and discrete data.
Okay, wait. I actually want to push back on something here, or at least admit my own misunderstanding.
Sure.
I always thought connecting data points with a line was just like a stylistic choice.
A lot of people do.
Yeah, drawing a line between the tops of a bar chart just to give it some visual flow and make the trend look cooler.
Yeah.
But the sources say that is a fundamental error. Why?
Because the line itself represents an assertion of fact.
Really?
Yes, a line graph is strictly for continuous data. Right. Think about tracking a patient's temperature over a 24-hour period. That line moving from 8 a.m. to 9 a.m. legitimately represents real physical values that existed in the universe between those times.
Because at 8:30 a.m., the patient had a temperature, even if you weren't there with a thermometer to record it.
Exactly. The line reflects the continuous flow of time and biology.
Okay, so the line signifies that the space between the dots actually exists.
Yes, but a bar chart is for discrete categorical data. Imagine you are graphing the number of patients with different blood types.
Type A, type B, type O.
Right, these are entirely separate bins. If you draw a line connecting the bar for type A to the bar for type B, you are visually claiming that there is a transitionary state between them.
Which is impossible.
Exactly. There is no such thing as a patient who is halfway between blood type A and blood type B.
Oh, wow. That distinction makes the cognitive trap so clear. You're implying data where none exists.
And that leads directly into a classic visual trap on the TEAS exam, which is confusing a standard bar chart with a histogram.
Oh, yeah. To the untrained eye, they look almost identical, right? Just a series of vertical rectangles side by side.
The visual difference is very subtle, but the conceptual difference is massive. As we just established, a bar chart compares separate, discrete categories like blood types or hospital departments.
Right.
The bars usually have gaps between them to emphasize that separation. A histogram, however, takes a single continuous variable and slices it up into equal ranges, known as bins.
Bins.
Right.
Okay, let's put that in a clinical context. A bar chart might show the total number of patients in the cardiac ward versus the pediatric ward, separate categories.
Correct.
But a histogram would look at, say, the blood pressure of every single patient in the hospital and show how many fall into the 90 to 100 range, the 101 to 110 range, and so on.
Exactly. And because that blood pressure scale is continuous, the bars on a histogram actually touch each other.
Oh, I see.
There are no gaps because the underlying number line has no gaps. Test writers exploit this all the time to see if you understand whether you are looking at distinct categories or a continuous spectrum.
Speaking of spectrums, we also need to tackle the mechanism of prediction, because the sources heavily emphasize the difference between reading within the data and reading beyond it. Interpolation versus extrapolation.
Right, these are two very different cognitive tasks. Interpolation is estimating a value that falls inside the boundaries of your existing data points.
Okay.
So if you know a patient's heart rate at 2 p.m. and 4 p.m., estimating the rate at 3 p.m. by looking at the line connecting them, that is interpolation.
Got it. And assuming the trend isn't wildly erratic, interpolation is usually highly reliable, right? It is grounded in surrounding facts.
It is. But extrapolation is venturing out into the unknown. It's looking at the trend and predicting what the heart rate will be at 8 p.m., well past your last measurement.
And the mechanical flaw of extrapolation is the assumption that the current conditions will just remain static indefinitely.
Exactly. Extrapolation is an educated guess. It is not a measurement. And nursing exams frequently test this boundary. If a question asks what the data proves, you can only use interpolation.
But if it asks what might probably happen,
Then it's asking for extrapolation.
okay, so we've covered the mechanics. But what happens when the underlying math doesn't match the visual shape we're interpreting? Like when the visuals actively deceive us, even when the math is technically correct.
Yeah, this is fascinating. To understand this terrifying disconnect between summary statistics and visual reality, we have to look at a famous demonstration called Anscombe's quartet.
Yes, developed by statistician Francis Anscombe in the early 1970s.
Right. He essentially proved that you cannot trust the raw numbers alone. He built 4 different data sets. If you run the math on these 4 data sets, calculating the mean, the variance, the correlation coefficient,
Right.
the summary statistics are perfectly identical. On a spreadsheet, these 4 data sets look like they are describing the exact same phenomenon.
Which is mind-blowing.
It is, but the magic happens when you actually plot the coordinates onto a scatter plot. The 4 graphs look radically different.
Radically different. Like how different?
Well, dataset 1 forms a neat, simple linear trend, gently sloping upward.
Okay.
Dataset 2 forms a perfect dramatic curve, like a rainbow.
Wow.
Dataset 3 is a perfectly straight line, except for one massive outlier sitting far away from the rest. And dataset 4 is just a vertical stack of dots, again with one extreme outlier off to the right.
Wait, how is it mathematically possible for a straight line and a massive curve to share the exact same statistical average?
It all comes down to the gravitational pull of outliers.
Gravitational pull.
Yeah, think of a regression line, the line of best fit.
Like a rubber band. I love this analogy. Like a rubber band stretched across a board of pins.
Yes. If you have a cluster of normal data points, the rubber band sits nicely in the middle. But if you introduce one extreme outlier way off in the corner, it acts like a black hole.
It just pulls the band.
It exerts immense mathematical gravity, pulling that average far away from the actual cluster. Anscombe's point was that summary statistics are blind to shape. An outlier can completely artificially inflate a correlation.
The takeaway there is foundational. Numbers lie by omission. You literally must look at the graph to see the actual shape of the real-world behavior.
You have to.
And, if we look at the real-world consequences of failing to visualize data correctly, my mind goes straight to the Space Shuttle Challenger disaster in 1986.
Yeah, a tragic example.
The engineers at Morton Thiokol, the company that built the solid rocket boosters, they actually had the data showing that the O-rings were sustaining damage on previous flights.
They possessed the data, yes, but they failed to communicate the gravity of it to NASA management the night before the launch.
Why?
While the engineers presented tables of numbers and these disjointed charts, they were trying to argue that cold weather caused the O-rings to fail. But their visuals did not clearly map the ambient temperature against the incidence of damage.
So they had the truth right there in their hands, but the visual format totally obscured it.
Exactly.
And the launch happened at a record cold 36 degrees Fahrenheit, and the shuttle broke apart 73 seconds after liftoff.
It's heartbreaking. And years later, the renowned data visualization expert Edward Tufte analyzed that exact same pre-launch data.
Right.
He didn't introduce any new numbers. He simply changed the visual mechanism. Tufte created a stark, clear scatter plot. He placed the temperature on the x-axis and an index of O-ring damage on the y-axis.
Here's where it gets really interesting, because suddenly the invisible truth becomes unavoidable.
Totally unavoidable.
When you look at Tufte's scatter plot, almost all the significant O-ring damage clusters sharply on the far left side of the graph where the temperatures are lowest. The trend is terrifyingly obvious.
It jumps right off the page. Tufte's core argument was that poor graphical design literally contributed to a fatal misjudgment. The evidence was just lost in the visual noise.
Because visual design can obscure life and death truths, statisticians and designers wage absolute war over how to draw these charts.
Oh, fierce debates.
Yeah, let's dive into those debates. Because we already discussed the magnifying glass effect of truncated axes, but another massive point of contention is the use of logarithmic scales versus linear scales.
Right, and this was heavily debated during the early days of the COVID-19 pandemic.
Oh, I remember that.
Yeah. A standard linear scale moves in equal increments, right? 10, 20, 30, 40. It shows absolute growth. But a logarithmic scale moves in powers of 10. 10, 100, 1,000, 10,000.
I always found logarithmic scales so incredibly confusing to read, like why even use them?
Because they are mathematically necessary to visualize exponential growth.
Okay, how so?
Well, if a virus is doubling every few days, a linear scale will just shoot straight up off the page like a rocket ship. You can't see any nuance at the bottom. A logarithmic scale compresses that massive vertical leap so you can actually see the rate of change.
So a straight line on a log scale means the growth rate is steady, even if the absolute numbers are exploding.
Exactly.
But the danger is how the public perceives that compression. Like, news outlets would switch to a log scale, and suddenly this apocalyptic spike in cases looked like a gentle, flattening hill.
Right. The visual curve looked flat, but the underlying numbers were still multiplying by thousands.
The choice of scale completely alters the emotional impact of the data.
It does. And exactly the same manipulative potential exists with dual-axis charts.
Oh, dual-axis charts.
Yeah, these are graphs where you plot two entirely different variables on the same chart, using a y-axis on the left for one and a different y-axis on the right for the other.
Okay.
By slightly adjusting the increments on one side, you can force a line representing, say, ice cream sales to perfectly overlap with a line representing shark attacks.
And it creates this visual illusion of correlation.
Exactly.
Which brings us to the golden rule you will see on every exam. Correlation does not equal causation.
Never forget that.
Just because two lines move in harmony does not mean one is causing the other.
So true. Now, there is one more debate that gets to the very heart of how our brains process visuals.
Great.
It's the great chart junk controversy, sparked by that same expert, Edward Tufte.
Chart junk.
Yeah. In the 1980s, Tufte introduced the concept of the data-ink ratio.
He basically argued that every single drop of ink used to print a graph should represent core data.
Right.
Like, if the ink is just being used for drop shadows or 3D effects or cute little illustrations of money bags, it's chart junk.
Exactly. And the mechanism behind Tufte's argument is cognitive load. Extraneous visual elements force your brain's working memory to sort the decoration from the data, slowing down your comprehension.
Makes sense.
So for decades, the entire field adopted his minimalist, stripped-down aesthetic.
But wait, I'm looking at a study in the sources from 2010, the Bateman study at the CHI conference. Didn't they completely challenge that?
They did.
Yeah, didn't they find that people actually performed better with the chart chunk?
They uncovered a really fascinating cognitive split. The Bateman study found that tough day was right about the short term. People could read the minimalist charts slightly faster and with high accuracy in the moment.
Okay.
However, when the researchers tested those exact same participants weeks later, the people who viewed the heavily embellished chart junk graphics recalled the data significantly better.
Because the visual embellishments hooked into their episodic memory?
Exactly.
The quirky drawings gave the brain something sticky to hold on to long after the raw numbers faded. So, what is the goal of a graph? To be mathematically pure in the moment, or to be memorable a month from now?
That tension remains completely unresolved in design circles. But for you, the listener, heading into a nursing exam, you must align with the tough day deal.
Right.
The exams do not care about your long-term episodic memory. They are testing your immediate mathematically pure extraction of data.
Okay, let's bring this all back to the real world. Why does this specific skill set matter long after you clear the hurdle of the exam?
Because it's not just theory.
No, because for a nursing student, graphicacy isn't just an academic exercise. It is a vital clinical instrument.
Absolutely. When you are managing a patient, you are constantly interpreting visual data.
Yep.
You are looking at electronic health records, tracking fluid intake and output over days.
Right.
You are monitoring glucose trend graphs. You are reading continuous fetal heart rate strips.
And if you look at a truncated axis on a vital sign flow sheet and panic over what looks like a massive drop in blood pressure when the actual numerical change is clinically insignificant, you are making the exact perceptual error that TEAS exam tests for.
And in the hospital, failing to check the axis causes unnecessary interventions.
Or conversely, misreading a downward trend in oxygen saturation as a minor blip just because you don't understand the scale.
Exactly. To protect against those errors, you need to internalize the core mechanics we've covered today.
Let's summarize them. The first defense is always manually verifying the axis scale. Is it starting at 0? Is it linear or logarithmic?
Your second defense is matching the graph to the data type. Remember the blood types versus the blood pressure ranges.
Right.
Bar charts are for discrete, separate categories where no in-between states exist. Line graphs and histograms imply a continuous, measurable flow.
Your third defense is knowing the boundary of the facts. Interpolating a value between two known points on a stable trend is a reliable extraction. Extrapolating a future outcome beyond the drawn line is an assumption.
Your fourth defense, never let a synchronized visual trend trick you into assuming causality.
Correlation does not prove causation without a controlled experiment.
And finally, rely on the Anscombe rule.
Yeah.
Averages and summary statistics can hide massive outliers and completely different behavioral shapes. Always demand to see the visual plot.
Always. Mastering these mechanics transforms a beeping hospital monitor from a terrifying jumble of lines into a clear, articulate language. But, the implications go far beyond the clinic.
They really do.
Nightingale proved that a well-designed graph can literally shift government policy. And Tufte showed that a poorly designed one can hide a fatal engineering flaw.
It's powerful stuff.
It is. Now imagine a future where artificial intelligence is instantly generating our charts and graphs for us, just scraping massive data sets and spitting out polished visualizations in seconds.
It's already happening.
If we lose the ability to critically read axes, scales, and outliers, who is actually deciding what the truth looks like? Are we entering an era where the AI determines the shape of reality before human eyes ever even see the raw numbers? Think about that the next time you accept a chart as absolute fact. Thanks for joining us on The Deep Dive.